So good afternoon, everyone. So most of the talk will be technical. I do have some demos towards the end of a text mining system that we developed at Clear Forest, which is a company that I founded. And I can show you if you are interested towards the end, but we'll see how we are on time. So this is totally unrelated to the demo. So let's start with a little background about information extraction. So there are two main approaches.
I think my viewer is trying to come in on a different line.
So somebody needs to press accept? Yeah. Okay. So there are two main approaches to information extraction. The first one is the knowledge engineering approach, which basically means that you write rules. You write rules, and that was the approach that Clear Forest took. We developed actually a dedicated language called DIAL, Declarative Information Analysis Language. It used to be declarative because I was a Prolog person, so the initial version was actually a logical language, but now it's actually much more like a C++ language, object-oriented, etc. But just the name stayed. And the approaches that are based on rule-based systems, in most of the competitions, prove to be the best approaches. We competed in 3 competitions. I told the people in lunch. 2 ACEs, ACE in 2002. So ACE, for people that don't know, stands for Automatic Content Extraction. That's the competition that is administered by NIST, supported by DARPA. And there are universities and institutions, think tanks that participate in it. So the first one was ACE in 2002. So we participated in the English task. There are 3 languages that they do: English, Arabic, and Chinese. So in 2002, we did English, we came number 1. In 2004, we did Arabic, came number 1. And in 2002, we also did the KDD Cup, which was about analyzing PubMed articles to identify when you find new information about genes of the Drosophila, the fruit fly. And we also came number 1. So basically, I think it just to prove my point that if you put enough effort into writing the rules, you can get the most accurate system. The main problem is that it does take a lot of time. You need really very good programmers in order to write the rules. And you need a very good engineering environment to support it, because you need to know how to debug the rules. And anybody that tried to work with rule-based systems know that there is usually they are very interconnected. So if you change one rule and you think that you solved 10 problems, you discover that you created 100 new problems. So it's really very hard to control how the rules affect each other. So you need all those really strong debugging and tracing and profiling systems. And the main problem is that it's language dependent. So it means that for each language that you want to work in, you need to write a different set of rules. The second approach is to use machine learning. So there, and this is the supervised approach. So there, you need to provide an annotated corpus. So you just provide like a richly annotated XML set of documents. And there are not so many that are available. The Linguistic Data Consortium, LDC, is the main body that provides all those annotated corpuses. And you can work on them. But if you try to count how many annotated documents we have, and this is about after 20 years of annotations, it will be a few thousands. That's it, not more than that. So that basically shows you that it's really hard to annotate documents accurately. It takes them a lot of time to do it, and in each annual competition that they create, each ACE, they just annotate 400 documents, 300 for the training data and 100 for the test data. So if after 20 years we have about, I don't know, 6,000 annotated documents, it tells us that there is a serious problem with this approach. Now, the good thing about the machine learning approach is that it's not language. It doesn't depend at all at the language. I mean, if I'll have an annotated corpus in Chinese, I'll learn it for Chinese. If I'll have it in Arabic, I'll learn it for Arabic. It doesn't matter. I mean, the algorithm doesn't care about the language at all. And in addition, if, for instance, in English, if I'm changing the capitalization, the orthography, I'll just rerun the system when I have the whole text in uppercase, and the system will learn to cope with text all in uppercase. In a rule-based system, usually you would rely on the capitalization, especially in the part of speech component, and then it would be a problem. You'll need either to write new rules or do other tricks that we try to do, but it's not a problem for the machine learning approach. You just retrain.
Don't you use it more to change the features somewhat depending on the language? Or
In the machine learning approach?
No?
We didn't, no. We just changed the training data and reran the algorithm. I mean, we'd use the classic algorithms, HMM, CRF, and
the algorithms don't care, but the performance would not matter, or features would?
there is some degradation, but not significant, like 1 or 2%, something like that. Okay, so I think it's clear that neither of the approaches is good enough. I mean, there are definitely problems with the rule-based approach. There are definitely problems with the machine learning approach, because you need all those hundreds of documents that you need to annotate, and as we said, it's not so easy to do them. Anybody that tried to do annotations in a very consistent way knows that it's extremely boring. And this is why it's so hard to get documents annotated. So then around 2004, 2005, several researchers around the world started to think about unsupervised information extraction. So one of the pioneers was Oren Etzioni in University of Washington, and they built the know-it-all family of systems. There are actually a few of them: know it all, know it now, know it whatever. So know it all basically is a system that can learn facts from the web. And I'll show you like 2 or 3 slides about know it all, and then this is just as a motivation for the work that we did. And I'll show you also experimental comparison between the results of the know it all people and the work that we did. So the main thing for know it all initially was just to do entity extraction, basically to create semantic lexicons out of the internet. So for instance, you want to know, you want to get list of composers, or a list of basketball players, or a list of scientists, or a list of cities, or a list of countries. So clearly cities and countries are much easier than list of composers and list of scientists. So I'll show you what was the main approach. So I'm actually jumping to the next version of know-it-all, because as I said, the initial version was just entity extraction. The new version that we compared against is the one that is able to extract relationships between entities. So basically it's built on top of the entity extraction component. So think about it as working like in 2 passes. The first pass, you identify the entities, and then you try to correlate between the entities. So they used what they call generic patterns. So they are hard-coded, and that's the main disadvantage that we try to fix. It's hard-coded, and they're not so flexible. So for instance, for acquisition, they use things like noun phrase was acquired by another noun phrase, or noun phrase's acquisition of another noun phrase, and there are some patterns for mayor, that a person is the mayor of a city. So clearly the good thing about this approach is that it will give pretty good precision, but the recall is lacking, because in many cases in the text it won't fit such rigid patterns. If you want to find something that is, you know, it will say Microsoft, the giant software from whatever. I know it's not politically correct to talk about Microsoft here, but it's fine. Acquired another, so you'll have so many words in between, those patterns will not catch it. So this was our motivation, basically to use pattern learning to try to get a system that will have the same precision, but much better recall. Okay, so that's what I'm going to talk about. So the system that we created is called SRES, stands for Self-Supervised Relation Extraction System. And there are actually 4 papers that we published about it. First one was in ACL, 2006. Then in EMNLP, 2006. Then some European conference, Intelligent ISMIS 2006. And finally, in ICDM 2006, just a month ago in Hong Kong. Okay, so what's the input to the system? The system takes as input the name of the relation that you want to extract, and the name of the relation may be like acquisition, merger, CEO, joint meeting, like one person met another person. So basically any relation that you might be interested in. But in addition, you should give also the types of the argument. So basically you give the schema of the relation. So the name of the relation and the types of the arguments. And the types of the arguments would be like a company, person, location. So basically the types of the named entities that are the arguments of that relation. I'll show you actually 2 versions. There is one version that relies just on a shallow parser that extract noun phrases, and a version that relies on a named entity recognition component. So there we need to extract also the types of the arguments. And you'll see that there is about 15% improvement when we use a named entity recognition component. So here is the architecture of the system. So I'll explain the architecture, and then later we'll go deep into each of the components of the system. So as I said, the input is a set of keywords that basically describe the relation. In many cases, it can be just one keyword, like acquire or merge. And that basically will use WordNet to find synonyms. And from that, we will start to build our corpus. So we will build the corpus just by we use the Google API to get the sentences. Major problems with it. I don't know if there's somebody that works around it, I'll be happy to talk to them, because it has like so many problems that we had to find some workarounds around it. Anyway, so as I said, we get the keywords, we get the types of the arguments of the relation. We get all the sentences that contain one of the keywords of the original set. So if it was like merge, we would find all the ways that you can put merge, merger, merged, and we will try to find all the sentences that contain any of the words. So this will be the initial corpus, basically sentences that contain one of the words in this initial keyword list, okay? And then the next step is to find seeds. So in order to find the seeds, we used the same generic rules that are used by know-it-all. The good thing about those patterns is that they have very high precision. So for instance, X acquisition, or basically we'll plug any verb inside of another noun phrase, and we will then get pairs of entities that have this particular relationship between them, okay? Now, we take only the top 10 pairs, so we count how many times we found each one of the pairs inside this corpus. And we take the top scoring pairs, and those pairs would be our seeds. I'll show you an example. What are the seeds that we got for the acquisition relationship? After we have the seeds, we find out of the original corpus all the sentences that contain one of the pairs. So for instance, a pair would be HP and compact. So we look for all the sentences that contain HP and compact. Clearly, inside the sentence, there would be also one of the words, if it's like acquisition, acquired, acquisition, acquired, I mean, all the variations of the word, and we'll have the two entities. So based on this set of sentences that contain the 10 pairs, usually would have like several dozens of sentences for each one of the seeds. So we will have a corpus of about 200 sentences, 400 sentences, something like that. And based on this corpus, we start the pattern learning process. Then we actually identify all the patterns that we have between the pairs of entities. And I'll show you exactly how we do the pattern learning. Then based on after we learn the patterns, we can do instance extraction out of.
I think they have a message for us. We get closer. Yes. Please change camera to include screen presentation.
Yeah.
Are we fine? Okay.
Can you hear us now?
So after we have the patterns, we can use the patterns actually to go back to the original corpus, that one that contained, in some cases, millions of sentences, and we extract out of the original corpus all instances that match one of the patterns. There's, on the way I'll talk about scoring the patterns, so we don't take really all the patterns that we generate, because we generate really tens of thousands of patterns. We just take like the top scoring 300 patterns, and we use those 300 patterns to extract all the instances. Then after we get all the instances, we use a predicate independent classification component to give a score to each of the extractions, to each of the instances. And based on that, we score all the instances that we have. This actually enables us to decide what is the threshold that we want to use. And of course, if we'll set a very high threshold, precision will be very high, but recall will go down. If we will go lower, then of course recall will go up, precision will go down. So I can actually draw the precision recall graph just by changing the parameter. What is the threshold that I'm using for scoring the instances? And I'll show you those results when we compared it to the performance of the know-it-all system. So those are, for instance, the seeds that we used for the acquisition relationship. It was generated automatically by the system, and you can see it's pretty good. The only thing that actually didn't work so well is this one, because it got also the San Francisco based, which is probably something that we should have gotten rid of. We didn't. But other than that, looks pretty good. Okay, so let's focus now on the specific components that we have inside the system. So the first component that I'm going to talk about is the pattern learning component. So we have all the sentences that contain the pairs that we built. Like for the acquisition, you saw the top 10 pairs that we used. And what we need to generate now is a set of positive examples and negative examples for the pattern learning process. Why do we need the positive and negative? Basically, to score the patterns, because we would be interested in patterns that cover mostly just positive instances. But it's very important that the patterns will not cover any of the negative instances. So positive instances, that's easy, right? We can just take the sentences that contain one of the pairs and generalize it into some positive pattern. But how do we generate the negative ones? So there are all sorts of ideas that people try to use, and we used some new ideas that we came up with. So, so I'll talk about them in a minute. So this is how we generate the positive instances. Here is an example of a sentence, this one. And basically we replace the arguments with attribute 1, attribute 2. I mean, here it's binary. If it was an n-ary relationship, then we would replace it with a set of attribute 1 till attribute n. So this is what the sentence would look like after we do the generalization. So I'm missing negative instances 1, okay. So here are some ideas how to generate negative examples. So one thing that was suggested actually by Ralph Grishman from NYU, and then also the people from Washington used the same technique, was that you should learn actually several relationships in parallel. So you don't learn just acquisition alone. You learn like acquisition, merger, CEO, mayor, whatever. And then the positive examples of the other relationships would be the negative examples of the current relationship. So that makes sense, but we wanted to do more. So one easy trick is if you have an antisymmetric relation. For instance, acquisition is an antisymmetric relation because you want to know who was the acquirer and who was acquired. So if you reverse it, you'll get a negative instance. In merger, it doesn't work because it's symmetric. So by the way, you'll see, it's very hard to distinguish between an acquisition and a merger because just in accounting, there is no clear distinction between what's an acquisition and what's a merger. So we saw, for instance, that HP and Compaq in many cases appeared as an acquisition. Other cases it appeared as a merger. So that definitely sends the system into some problems. I'll tell you about the next generation of the system, which is totally unsupervised, and there definitely we had issues with it. So finally, we just put them in the same cluster. Okay. The other, and this is what is written on this slide, the other trick that we did and actually boosted our precision a lot was to take the sentences and identify inside the sentences all the noun phrases. And then basically change the assignment of attribute 1 and attribute 2, in the case of the binary relationships, to the other noun phrases in the sentence. So basically, let's say you have 5 noun phrases in the sentence, and let's say that the correct ones are the last 2. So I'm taking one and I'm moving it to the first noun phrase, taking this and moving it to the third noun phrase. Of course, there are many combinations that you can do. Each one of them is a negative instance. The good thing is that you're using the same vocabulary of this relation. You're not using a vocabulary from another relation, because one of the problems that we saw is when you try to learn from other relations, but using their vocabulary, actually not a good negative instance. Usually when you try to do a classification, you're interested in near positives. And the way that we describe generates much better near positives than just using other relationships as your negative set. As I said, we have 2 modes of operation. One is the shallow parser mode, where we just generate noun phrases. And the other mode is a mode where we also do the named entity recognition. So if we have the named entity recognition, we will change a company for a company and a person for a person. If we have the shallow parser mode, we will change a proper noun for a proper noun, a general noun phrase for a general noun phrase. So basically, we keep the typing scheme to try to be as near positive as possible. So here are some examples. So this is another example of a sentence where we replaced, again, the names of the entities with attribute 1 and attribute 2. And here are some negative instances that we can, by doing the swapping that I just described. Okay, so is that clear? And as I said, we can use this symmetric and anti-symmetric. So in symmetric relationships, if we swap the order, we'll get another positive instance. In the anti-symmetric, we'll get a negative. So now we get to the pattern generation mode. And in this mode, basically we take any pair of sentences, any pair of generalized sentences, and we try to find the most specific generalization of the two sentences. So this is, the classic dynamic programming algorithm, how to find the least common generalization of the two sentences. And I'll show you an example how it works. First, before I'll show you the example, I need to say a couple of words about the pattern language that we use. So the patterns in this case are sequences of tokens, just words. Skips, we have two types of skips, unlimited skips. So basically you can skip any number of tokens, and limited skips that can skip only until they find another noun phrase. So they are not allowed to skip over a noun phrase. And that actually helps a lot to restrict the patterns that you get. And in addition, of course, we have the slots, the arguments of the relation. So if it's binary, we'll have only 2 slots. N-ary will have more accordingly. So here are some examples of patterns. You see attribute 1, skip was acquired by attribute 2, etc. So at this point, I want to say a couple of words about anchoring. You can look at the slots. I mean, what's written here is attribute 1, attribute 2. And in some cases, you can see that attributes are not anchored. It means that next to them, you have a skip, which means that you don't have a clue exactly when the attributes, where is the attribute inside the sentence. So if we have slots that are anchored from both sides, that's the best. It means that really the precision will be very high. So later, when we do the scoring of the patterns, we will utilize this information. So patterns that have anchored slots will have higher scores than patterns that don't have anchored slots. Okay? And you can see since we have 2, then we have the scoring for 2 of them are anchored, only 1 is anchored from 2 sides on 1 side. So we have basically 3 levels. We have unanchored, we have semi-anchored, and fully anchored. Okay? So we talked about the generalized function, and basically to do the dynamic programming, I just need a cost function to define what would be the cost of matching any 2 elements. So of course, if the 2 elements are identical, the cost would be 0. And then we have other costs that really doesn't matter what is the exact cost function, as long as qualitatively it maintains the relations that we have here. So let me show an example. So this is the first sentence. Towards this end, argument 1, attribute, doesn't matter, in July acquired argument 2. And then earlier this year, argument 1 acquired argument 2. Okay, so you see it's similar sentences, but not the same. So toward here in the first sentence doesn't match anything on the second sentence. So we have a cost 2. Then earlier here doesn't match anything again. This matches this, so it's cost 0. And of course, argument 1 and argument 1, of course, always need to be matched to each other. They cannot match anything else. It's an infinite cost. And based on the dynamic programming, we find that this was the best match. And yes?
But how do you decide in the cost and the dynamic programming, where is in July 2 times as expensive as 2 words?
Because it's 2 words. In and July. Yeah, I probably should have put it in 2 lines. Okay. So this is like the pattern that we will get. And now you can do pattern simplification, because 2 skips is 1 skip. I mean, doesn't make any difference. And clearly, when you have a leading skip, you're also not interested in it, because inherently, any pattern, you'll have a leading skip. So you don't need this. And in addition, that this is like a stop word, so we can just remove it. And basically, the pattern will start with the comma here. So that would be the pattern that we got from the previous 2 sentences. Questions about this? After we have all the patterns that we generated, yes?
So you do this pairwise for all pairs?
Yes. That's the old version. In the new version, actually, we took one of the classic data mining algorithms, the a priori algorithm, and we did it in a different way, much faster. It's actually more sequential patterns, and that gave us a huge boost in performance. One of the things that we do after we generated the patterns is to look at the pattern and see if one of the original keywords is maintained in the pattern. If we do not see any of the original keywords, I mean, after we expanded it with WordNet, then it means that this pattern doesn't have any substance. I'll show you an example in a minute. And then we delete this pattern. Only patterns that have at least one of the original keywords or one of the synonyms will be maintained. Okay? So for instance, you can see here in the first example, this doesn't contain anything, any acquired, acquisition, bought, purchased, nothing. So it has 0 value, so we just delete it. Here, it says purchased, which is one of the synonyms of the original keywords, and this is why it's kept as a pattern. And now we do the scoring of the patterns. We have positive and negative examples. And I mean, the formula doesn't matter so much. We played with different types of formulas, how to do the scoring, and it didn't make such a difference. The only thing you care about is that you want to have as many positive examples that will be covered by the pattern and almost none of the negative examples. So this was a pretty good scoring function, and this is what we use. And then what we do is we take the top 300 patterns, and this is our pattern set. So here are some examples of patterns that we found. This is like for inventor, that X invented Y, which is not such an easy. I mean, here, the initial version was written in Perl. So, you know, in Perl, the dot is something that matches any character. So the dot star is basically just the skip. And this is for CEO. Okay. For the shallow parser, initially we used the OpenNLP, which really sucks. And then we didn't use it anymore. I mean, it's too slow. And what we did is we used our own version of CRF-based noun phrase extractor, which works about 10 times faster and is more accurate. So let's summarize where we are now. So now we have all the patterns that we extracted. I mean, the top patterns after we scored them. We took the top 300. We went to the original corpus that in many cases contained around 1 million sentences. And we pulled all the instances that matched one of the patterns. Now we want to score the extractions, because some of the extractions will not be correct. So we want to rank also our extractions. And for that, we wanted to build a classification model. Now, usually when we talk about classification, that sounds like supervised learning, which means that we need the training data. Now, if we need training data, that would be probably predicate dependent, relation dependent. So we cannot assume that we can train for each relation, give examples of the relation. That basically kills the whole approach. Yes?
Sorry, could you clarify, you said now you're going back to original corpus, which has millions of sentences.
Yes.
Are they the sentences that you gathered from the web, or are they
From the web.
How did that end up being millions of sentences? I thought you...
Basically, any sentence that would contain one of the keywords, like merge, merger, not the ones that are related to the seeds. We started with a big corpus that contained just sentences that contain any of the keywords.
So you do a Google search and then...
Yeah, this is what I said, the Google API.
And go through every page of results and...
Correct,
sentences.
yes, yes. Of course, you know, Google returns only 1,000 hits per query, so you need to start to play, you know, to add words, all the usual tricks. Even with the usual tricks, there are problems. But yeah, finally, after a painful process, you get to a very large corpus. That was definitely one of the most difficult things. I'm sure internally, that's something that probably I'll not have a problem with. So
Definitely not.
yeah, so that will be a relief. So basically, as I said, to build the training data for each predicate is out of the question. So we want to move to a predicate. When I'm saying predicate, I mean relation. I mean, I'm using them interchangeably. We want to move to a predicate independent version, which means I'll do the training only once for one predicate, and it will be used for any other predicate. So initially, it doesn't sound that it's going to work, right? But you'll see. Okay. So here are some of the, so in order to do the classification model, we need features. So we want features that are predicate independent. We cannot use anything semantic, because anything semantic will be predicate dependent. So we need to use only syntactic features of the patterns. So here are some examples of features that we used. So the first one was just how many different sentences supported the pattern that generated the instance. So if we have a lot of sentences, that's good. Then about the pattern itself that generated it, how many positive and how many negative examples this pattern matched. So of course, the higher the number of positive and the lower number of negative, that would be a good thing. About the anchoring, I told you about the anchoring before. So of course, patterns that have only slots that are fully anchored would be better than pattern that includes totally unanchored slots. How many non-stop words the pattern have? If we have more non-stop words, it means the pattern is more specific, and then we give it a higher score. If there are proper noun phrases in between, I mean in the skips. And finally, in the skips themselves, how many words matched the skip. And again, the rationale here is that if we have many words that match the skip, means the skip was longer, usually it would mean that probably the extraction has a lower probability. We would give higher probability to shorter skips, okay? Again, those are the 6 features that we thought about. You can think about maybe another 6, and we can add it to the model as easy just to try and see if it works better. But as you'll see, it works pretty well for us, so we didn't really see an urgent need to think about additional features. But definitely, if somebody has ideas for additional features, I'll be happy to hear. So we used the logistic regression implementation that was done at Rutgers, David Lewis and his colleagues. It's called BBR. People probably are familiar with that, which has similar performance to SVM. SVM is actually a little better. Not by much, but it is a little better. We actually did some extensive experiments recently, and we saw that SVM was a little better than BBR. So BBR actually is a regression model. So we had to convert all the numbers into binary numbers. So this is how we basically did the discretization from the numeric numbers that we got before to the binary numbers. So from the 6 features, I mean, you can see the 2 and 5 we throwed, and we converted it into 15 binary features.
Sorry, what are you classifying? What is the prediction?
Well, it's actually more than classifying. It's actually, we get a number between 0 and 1, which is what's the probability that this is the correct extraction, that this is really an instance of the relation, okay? So if you set the threshold, if it's above the threshold, you classify it as a correct instance. If it's below the threshold, you classify it as an incorrect instance.
So you didn't have any training materials. Where's the
Right, so this is, I'm getting to it. I said we don't have training material for just any predicate, but we pick one predicate. And for that predicate, we do give training material, okay? But we use it for all the other predicates as well. So we do it once, and it's used for any of the other predicates. Okay. In addition, we also use the named entity recognition component. So, so I think I talked with Ryan this morning, and he mentioned that you're using some rule-based component to do named entity recognition. We actually also used a very simple rule-based named entity recognition component. It's actually amazing how simple it was. It was like 2 or 3 rules for each of the relations, and it worked well, I mean, in this context. We do want to do some other experiments where we don't use just this low-level rule-based component, but also like CRF and the better models for entity extraction. So we used this very simple component. In this case, for the relations that we picked, we just used it for person and company. So those are the only types that we were able to recognize. Of course, if you want to support other, you'll need to write specific rules or train on those entities, those types of entities. Okay, so I mean, it's not really important, the specific scores of the named entity recognition, but the main thing is we converted it into one additional feature. So previously we had 15 binary features, now we added another feature, and that created a better classification model. Okay, so one of the major questions that we wanted to explore was really, can we train on only one predicate, and can it be used for all the other predicates? So that was one of the key questions that we wanted to check. And what is the benefit of using the named entity recognition component? So the 16 features rather than the 15 features. And then, of course, to see if we are any better than the know-it-all system, the know-it-all that was adapted to extract relations, not only entities. So they actually had 2 versions. They had the original know-it-all and an improved version called know-it-all PL that was also able to learn patterns. So remember, initially when I started to describe know-it-all, I told you that they have only a very limited set of very rigid patterns. So they extended it by learning patterns. And you'll see all the results here. And the last question that we wanted to ask was, what is the true recall of our system? That's a problem, because all the time we just talked about precision. But to measure recall, that's pretty hard. Like if we have a corpus of 1 million sentences, I don't have slaves that can go over the 1 million sentences and tell me what are all the extractions that you can get out of it. So measuring recall is almost impossible. So we still found the hack how to go around it. What we did is there is a commercial database called the Platinum something that I got from my friends from NYU, and they have the subscription, and they gave me all the mergers and acquisitions in 2005 and 2006 when we ran it. And then I could actually compare, at least get an estimate for the recall in the following sense. I took all the list, and there were like, I think 40,000 mergers and acquisitions just in 2005. It's amazing. So we went over the list, and for each one of them, we looked if there is at least one sentence in the corpus that contains both arguments. Now, we didn't look if it's really a true instance of like acquisition. The only criteria was if I have a sentence that contained those two arguments. So basically, we're actually being too harsh on ourselves, but that was the experiment. So if we managed to extract that instance, then we got 1. If we didn't manage to extract it, we got 0, and basically this is how we measured the approximate recall. Okay? Sure.
Suppose there was a merger. You found one instance, but actually 10 instances of 10 different news articles about this merger. You found one, you are happy.
Yes.
But it could be that your recall is only 10%.
Correct. That's the difference between a classic information extraction system and a web extraction system. This is what we are comparing again. A web extraction system, you just care to find at least one instance of each event or each relation. Maybe it appeared 20 times, I don't care. If I picked once, it's good, because basically we just want to collect facts. So if the fact appeared 20 times, but I identified it only once, that's fine. I mean, maybe if you want to find all possible instances, that's a different problem. Then it's a classic information extraction system. But in this context, we are interested mainly in building a database of facts. We're not interested in finding the true recall of a true information extraction system. Although I must say that don't think that if it was 20 that we found one. Usually we found like 16 out of the 20. So it's true that we didn't do the full measure, because for that I will need all those slaves to go one by one. And unfortunately, I don't have them. But based on a very small number of experiments that we did, we get pretty good recall. So let's talk about how we do the training. So we picked one of the relations. We ran that relation over like 1,000 documents. 10,000, sorry. 10,000 sentences, not documents. 10,000 sentences. And from that, we got something like 200 or 300 extractions. And then manually, we went over the 300 extractions and said yes or no. Is it the correct instance or not? And this was our training data. So this was our training data for one particular relation. For that, we built the model, and then we used the same model for all the other predicates. Okay? Now, how did we measure the precision for the other predicates? Just by using sampling. Let's say that we extracted 10,000 instances. We picked 200 out of the 10,000 instances and manually checked if they are correct or not. Okay, I think I talked about that. So here's a sample of the output of the system. So you can see here, this is like HP and Compaq, and you can see all the sentences where we extracted. You can see the merger and acquisition is written in all sorts of different ways, and all of them appear. Is that a good thing that it appeared? Okay. So let's talk about the cross-classification experiment. So here, in each case, we used, here, the predicate that we used to do the training was acquisition. And you can see the results when we use this as a model on all the other predicates. And this is when we used a merger as the training predicate, and the result that we get on all the other four, I mean, including also merger. So you can see that qualitatively, it looks very similar. I mean, of course, there are some differences, but it looks similar enough. And we got the same performance when we used any of the other 3 predicates. We had 5 predicates in all: acquisition, merger, CEO, mayor, and inventor. Those are the 5 predicates that we tested it on. The X is the number of extractions, number of instances that were extracted. So here, this is the experiment that we did in comparing to know-it-all and know-it-all PL. So you can see here we have 4 systems. So this is know-it-all, know-it-all PL, the original version of Estres when we did not use the named entity recognition component, and here when we use the named entity recognition component. So as I said, we get a precision recall graph just by varying the threshold. So we have all those instances that get the scores, and we just vary the threshold, and this is how we get the different points. And you can see that pretty much this version was the best. I can tell you that in most of the predicates, on the same precision level, our recall was 3 times better than the know-it-all system. 3 times better, that's a lot. So it means that we found like 8,000 extractions rather than 2,500. So that's pretty major. It's not, we're not talking about like 1 or 2%, and at the same precision level. So these are for the other predicates of CEO of and mayor of, and this is for inventor. By the way, you see for inventor that we don't have the named entity recognition component. Yes?
Did you get the code for know-it-all to rerun their experiments on your?
No, they ran it.
Oh, okay.
I mean, we shared the sentences, and they ran it.
Oh, okay, fine.
Yeah. It was a true collaboration.
Okay.
Yes. So anybody has a guess why we don't have the Estres with named entity recognition in the inventor case? I mean, I showed you 4 graphs in all the other cases, so why am I showing you only 3 here?
One of the arguments isn't an identity.
Right. I mean, for invention, we don't have the capability to identify that it's an invention. I mean, we don't have a named entity recognition that is capable to do it, so this is why we didn't have this. Yes. Okay, so in general, why is our system better than know-it-all? So we actually try to really understand better when is it working significantly better and when it's similar. So what we found is that if there is a lot of redundancy, if there is a lot of redundancy, then know-it-all is doing well too. This is actually, it relates to I don't know, your name, your question. Because if they were able to find 1 instance, even if you had like 20 instances, and they found only 1 out of them. So if we had a lot of redundancy for the specific fact, usually they were able to pick it up too. We were able to pick it up even if the redundancy was very small. So for facts that were very widespread, very well known, know-it-all picked it. For facts that were little known, we were able to pick it much more than they were able to pick it. So if you think about it like for intelligence purposes, usually you'll have the interesting things only once. And that means that something like know-it-all probably will not be good for that. Now, the main difference, of course, comes from the pattern learning component. In their system, they use the fairly simplistic pattern learning. We use the more elaborate pattern learning. And this is why we were able to find many more instances than the simplistic approach. So this is, you can see the redundancy here. You can see that for mayor, the redundancy was very high, and this is why know-it-all did almost comparably to our system. And for acquisition merger, the redundancy was much lower, and this is actually where we excelled in comparison. So I told you about, so exact name of the subscription is the SBC Platinum. This is where we got all the acquisitions and mergers from. Talked about that. So you can see here that if something appeared only once, then in merger we're able to get it 50% of the time. In acquisition, only about 38% of the time. And as we get to like 8, we are able to get to higher than 80% recall, which is not bad. I mean, for many of the facts, many of the well-known facts, they appear like hundreds of times. So here 8 is usually something that is not very well known. Okay, so here are the conclusions. Let's talk a little bit more about actually the future plans, which I think would be more interesting. So one of the things that we're working on now is extending it to n-ary relationships rather than just binary. And in addition, we want to move to a totally unsupervised mode. Remember, the input in this case was the name, several keywords that describe the relation, and also the schema, like how many arguments and what are the types of the arguments. So in the next version, this was actually the paper that we published already in ICDM, we started with just a corpus, with nothing. And we tried to identify first the names of the relations, and then later learn for each of the relation, use Estres as like a subcomponent. So we have basically 2 phases. The first phase is relationship identification, and then relationship learning after we identify the relation. And it worked so-so. I mean, we're definitely not there yet. It was interesting enough, I guess, to get accepted, but there is a lot of work still that we need to do in order to get to a real commercial system that will be useful. I mean, when it's totally unsupervised. I think for SRES, it works pretty well. Definitely there are ideas how to improve it even more. Now, I don't know if I have time for demo or...
I'm sure that actually a lot of people have other meetings, unfortunately.
Okay.
So at those, I think we should take some questions, and then maybe if somebody wants to see a demo, they can stay afterwards.
Okay.
Because otherwise,
Sure.
I'm afraid we should. But let's start out by thanking the speaker at least.
Question?
Yes.
You may have mentioned this. When you train your classifier, this syntactic classifier, which one did you train it on with the predicate? Like you said,
Well, we tried all of them.
And so did you end up picking one? Or?
Yeah, I mean, for the final experiments, we picked acquisition.
That was actually your least frequent in the data sets?
Yes. Less redundant. Right? Least redundant.
So do you have any indications? You mentioned you just trained on one particular relation.
Right.
And a lot of these supervised algorithms, like logistic regression, you know, have a tendency to overfit to a specific domain or a specific problem. But it doesn't seem like it's happening here, right?
Because it was purely syntactic features. It had nothing to do with the semantics of the predicate. I mean, if the features would depend, you know, on the specific wording, then it would be horrible. But we basically look just as the structure of the pattern, you know, like how many words match the skip and how many non-stop words I have inside the pattern. So those are purely syntactic, just trying to evaluate the goodness of the pattern. And that's pretty general. This is why I think it was good for all the other relations.
Did you try using maybe a little more lexical features and then seeing it overfit? Or?
No, we didn't. No.
But did you ever also try to throw in 2 training sets? I mean, since you're going to use the same classifier and everything at the end, why didn't you train in both acquisition and merger?
That's possible.
I mean, you have the data.
I do. That's possible.
So is your approach applicable to other domains, in a sense, your text is basically business news. Is there any kind of property in business news, for example, the uniqueness of HP and Compaq, that lets you learn new patterns? Could it be that if you use it on other kinds of news with words which appear very, that in politics, you have names of nations, and you have many false positives like Israel and the United States may appear in so many contexts, not with a particular predicate, with many other predicates which are completely unrelated. Could it be that your system will mislearn something?
Yeah, it might be. It might be that there will need to try and use other mechanisms in order to. But remember, we are starting with sentences that contain one of the variations of the original relation. So the fact that Israel and the US appear in so many different contexts is not such a big problem, because I'll pick only the sentences that will contain, I don't know, let's think about the relation.
Okay.
Agreement, treaty, whatever.
Okay.
And I'm sure that we all have built-in questions we actually could keep asking you about. So, but maybe we should, since we're running a little over time, we should end it here so we also do not completely drift off the schedule. And,
Okay.
but thank you so much.